This is the second part to chapter 16.3. I'm doing it as its own video just because it's kind of its own topic and process all in one. But that is the process for finding that potential function we talked about when we want to evaluate maybe the fundamental theorem of line integrals, right? So just as a review, the fundamental theorem states that if f is a conservative vector field, then the line integral over f is just equal to the difference between the potential function of f evaluated at the endpoint minus the potential function at the initial point. So what we can do is this means that f is a conservative vector field. So it's a conservative vector field, and this little f is the potential function. So the question we have here, so the idea is, how do I ungradient f in order to reconstruct the initial function, right? So we know that we got, right, this conservative vector field came from taking the gradient of little f, right? But we don't know what this little f is. So we need a way for ungradienting the vector field in order to reverse engineer what that initial function was so we can evaluate it at b minus a. So that's what we're going to do here. So we need to be able to find the potential function. So it says here in example 1, we're going to find the potential function of f, right, our vector field, given that it's equal to this. And I know this is really big and ugly, but we're going to be able to reconstruct it. So the first thing I want to do is I just want to test to make sure this is even conservative, because it said if it's not a conservative vector field, it won't have a potential function that even exists. So let's first test if f is even conservative. And we'll do that using the component test, right, which was the derivative of p dy must be equal to dn dz. So that was the first one. And what did that equal? So the derivative of the p function, right, the last one, with respect to y, in this case is just x. And the derivative of n with respect to z, which in this case, with respect to z, is also just x. So this one checks out. That one's good. Let's try the derivative, the partial derivative of m with respect to z needs to be equal to the derivative of p with respect to x. And in that case, dm dz is going to be y. And dp dx, that's also going to be y. So it's looking good so far, so that one's good. And then the very last one was dm dy needed to equal dn dx, which in this case, dm dy is going to be, it looks like negative e to the x sine y plus z. Yeah, that's kind of big. So negative e to the x sine y plus z. And then let's check dn, right, the derivative of the n component with respect to x. That's going to be z plus e to the x cosine, oh no, actually it's with respect to x. So this is just e to the x sine y. Yeah, negative e to the x sine y plus z. So that checks out as well. So we know that f is conservative, in fact, because all three of those equalities are true. So f is conservative. Conservative. So we know, so a potential function does exist. and that will be in the form, the gradient of the potential function is equal to what we have up there. Right, so we need to ungradient this in order to find just f by itself. So we know in this case, the gradient is equal to the partial derivative of f with respect to x. That's the I component. Right, so we know that this is the gradient. So this has to be equal to df dx. This has to be equal to df dy. And this is df dz. And we know that because this is the gradient of a function, because we know it's conservative. So we can write that out here. We'll just start with df dx must be equal to e to the x cosine y plus yz. So if that's what the derivative of f with respect to x is, now we can start reconstructing piece by piece what the full potential function is. So the first step to do is we're just going to integrate this first equation with respect to x and get our first piece of the equation. So we're going to we'll integrate with respect to x. So we'll integrate df dx with respect to x. And what does that give us? So that will become just e to the x cosine y. So that's the integral of that. And now we're used to, when we evaluate indefinite integrals, right, we usually add on a plus c, right, plus a c constant. But what's different in multivariable integration like this is that this implies that the constant is just a number, right? And so when you take the derivative, it would just turn to 0, so you can't reconstruct it. But in this case, not only do constants evaluate to 0, but also any variables with respect to y or z. So anything that's just in terms of y and z's will also become 0 too. So those might have been baked into the original function that we don't get carried over when we take just the x partial derivative. So in this case, instead of just adding plus c, we actually need to add something called plus g of y and z, which is saying that the function, right, the potential function, could have had any other functions in just terms of y and z, that when you take the x partial derivative, they would have gone away, right? So that is how we reconstructed that. Oh, excuse me, I missed a whole term. So it's actually plus yzx, so xyz, plus that, right? So when you take the x partial derivative of this, right, you'll get that first component. So we know that this is our first iteration of the potential function. What we can do now is we can now calculate what df dy is. So find df dy of this, right, of our potential function, and it better be equal to what we know df dy is. So let's just calculate what that first derivative of f with respect to y. And so in this case, it would be negative e to the x sine y plus xz plus the derivative of this g function with respect to y. Right? And so now we compare it to, so now we take this and we compare it. Compare it to f. Right, so we know that we just kind of constructed this df dy from our potential function, and we know that it needs to be equal to this. Right, so in this case it's xz minus e to the x sine y. So this told us that the derivative of g with respect to y is equal to 0. So after comparing, we know dg dy, so that function in terms of y's or z's, must be equal to 0. Okay, so that's pretty good. So we know that there's no y components. So this tells us there's no extra y's. There's no extra y variables in that constant we added at the end in g. So it's just it is just a function of z alone. All right, so that's what that told us. By comparing the y partial derivative over potential function with the vector field, we found out that the derivative with respect to y of this extra function is just 0. So there are no y's hidden in here, right? That's what that told us. So now we're just going to do the exact same thing with df dz. So now we'll find df dz from our potential function and compare it again to the vector field. All right, so now we're going to find, so we'll find df dz, which in this case is going to be, that's just xy plus the derivative of g with respect to z. Okay, and now we'll compare it to f again. So we'll compare to f. So we know that this better be equal to this, right? So in this case, we know that dg dz must be equal to just z. So that's what this told us. So it told us about that constant of integration. So we know dg dz must be equal to z, and then we can integrate both sides, right? So then that function at the end, in this case, is equal to z squared divided by 2 plus c, right? And so we got that by integrating both sides. And so now if we want to reconstruct the whole potential function, right? So this told us, right? This is now what gets added on to that g component here, right? And so these two steps, we're just finding out what that extra constant of integration was that we couldn't necessarily construct from the beginning. So now we know. That f as a function of 3 variables is equal to, right, we'll start up here, right, that we got at the very beginning. So f is equal to e to the x cosine y plus xyz plus our constant of integration that we found at the end, which is z squared over 2 plus a constant c. There's our potential function. And we know that the gradient of this guy is going to be equal to our initial vector field. And so if we wanted to evaluate the line integral of this function, that is going to be really, really hard. Right? There's a lot of cosines, there's two trig functions, there's a lot of things being multiplied and added together. You'd have to do it 3 times. And your path of integration, this might be really complex. It might be like a squiggle line, or it might be the sum of 2 different paths, right, that are maybe that form 2 line segments. And so this is really nice because we could just ignore what the path is and just use the potential function we found to evaluate the endpoints. So we would just plug in the final point into this function minus the initial point in this function, and that will tell us what the line integral was, no matter what the path connecting the 2 points was.